Welcome to another video for Lambda class. In this episode, we're going to discuss Lagrange interpolation. And this is a very important topic when we want to talk about cryptography using polynomials. And it will build up on the basis of Euclidean division. Okay, so we're gonna start with a remainder. Okay, so let's recall one of the corollaries of Euclidean division. So let f be a polynomial with coefficients in a field. So and let A be an element of the field. Okay, so we have that A is a root for f if and only if x minus a divides f. What does this mean? That f of x can be written as x minus a times a polynomial h of x. With degree strictly one less than the degree of f. The degree of h being the degree of f minus 1. Okay, so there's a correspondence between roots of a polynomial and factors of a polynomial. A is a root for f if and only if x minus a is a factor of f. Okay, so this correspondence is very important, and we're going to build on this. Okay, so we're gonna extract a lot of juice out of this correspondence. One of the first things we are going to do is we're going to prove a theorem which is very important for us, especially when we work with coefficients in the field. Okay, so one theorem, which is really a corollary of Euclidean division. Let K be a field. You can think of rational numbers, real numbers, finite fields. There are plenty of examples of fields. And f belonging to K of x with degree n. Then f has at most k roots in K. So a polynomial of degree n has at most n roots in its base field. Okay, and we're gonna try a proof for this. So why is it that this is true? So let's try induction on n. Let's try induction on n. So let's try the base case. We need to establish the theorem for n equals 1. So we need to prove that any polynomial of degree 1 has at most one root in K. So let f of x be a polynomial of degree 1, so which is of this form, with obviously a sub 1 not 0. And let's solve f of x equal to 0. So how do we solve this? Well, in this case, it is easy, because a0 plus a1 times x equal to 0. We can find roots by isolating x. We're going to solve for x. Solving for x minus a naught, and then we, since a1 is not 0, we can divide, and x ends up being minus a naught over a1. So this is the only solution to f of x equal to 0, then it is the only root. For f. So this says that the theorem is true for n equal to 1. So we have proven the theorem in the base case, okay, for polynomials of degree 1. Now let's go to the inductive step. The theorem holds for all polynomials of degree n. This is what we hold to be true now. Theorem holds for all polynomials of degree n. We need to show that it holds for all polynomials of degree n plus 1. So in order to do this, we're gonna assume that the theorem is not true for polynomials of degree n plus 1, and we're gonna derive a contradiction with the orange part. So on the contrary, assume there exists a polynomial f with coefficient k of a degree of f being n plus 1, which has more than n plus 1 roots. N plus 1 distinct roots. So let's say that the roots are m0, m1, and n plus 1. These are the these are the roots of f for this assumed polynomial f. And using what we have seen in the first place, using the correspondence between roots and factors, then f has x minus m sub n plus 1 as a factor. Because there's a correspondence between roots and factors. So what we have now is that f can be written as x minus m sub n plus 1 times a polynomial h of degree exactly 1 less than f. degree of h is exactly n, right? So let's see what happens with h. Since all the m sub j's are roots of f, then when we evaluate f at m sub j, what we get is m sub j minus m sub n plus 1 times h at m sub j. Right? What does this mean? Since all these m's are roots, this calculation has to yield the number 0. That happens because all the mj's are roots. But these guys are non-zero, since all the mj's are distinct. So since we're in a field, since K is a field, then what happens is that this number needs to be 0. For 0 at most j, at most n. So this means that h is a degree n polynomial with m0, m1, m2, m sub n roots, which are exactly m plus 1 roots. And this is absurd. Because the theorem was true for all polynomials of degree n. Because this contradicts the inductive hypothesis. Where does this contradiction come from? Well, this contradiction comes from the assumption that there exists a polynomial of degree n plus 1 which has more than n plus 1 distinct roots. This is where the contradiction stems from. So there is no polynomial of degree n plus 1 with more than n plus 1 roots. So this proves the inductive step. Okay, so theorem holds for all n. Now, this is a very important thing to have in mind. Okay, a polynomial of degree n has at most n roots in the base field. It can have less, but it can have no more than its degree. Observation. A polynomial of degree n can have less than n roots in its base field. It's certainly the case in many settings. For instance, examples. Okay, let's consider f a polynomial with real coefficients and with this specification. Okay, this polynomial has degree 2, the degree of f is 2, but has no real root in R. So it might well be the case that we have a polynomial of degree n which has no roots at all. It can happen, but it can never happen that has more than its degree number of roots. Okay, the same happens in every other field. Okay, we can construct polynomials with no roots in a certain field. Okay, in most cases. There are some cases in which the fields are what we call algebraically closed. That means that every polynomial has a root in there. A field in which every polynomial has a root is called algebraically closed. There are algebraically closed fields, and there are fields which are not. Examples? Well, R is not algebraically closed. Since we have here an example, this polynomial has no roots in R. Then C, complex numbers, is algebraically closed. Every polynomial in C has a root in C. That's a very important theorem in the theory of fields. Okay, so it might well happen that we have less roots than its degree, but we definitely cannot have more roots than its degree. Okay, so this is very important because if we have a bound of the number of roots in the base field, then we have a way of actually deciding how similar can two polynomials be. This is going to be a very important conclusion from this theorem, and we're going to use it very, very much, and it's going to give us food to talk about some other things that go right towards interpolation. Okay, so corollary. Let f and g be two polynomials in k of x, both with degree n. Okay, then f and g coincide at most endpoints. Okay, two different polynomials. So if we pick two different polynomials, they cannot coincide at n+1 points. They have to coincide at most n points. Let's go for a proof of this. If f and g, if f and g coincide at M1, M2, let's start at M0, M1, M2 up to endpoints. Then the polynomial h of x, defined as f minus g, has M0, M1 up to Fn roots. All right. So f being different than g implies that h is not the zero polynomial. So what this says is that h is a non-zero polynomial that has n+1 distinct roots. H is a non-zero polynomial with more than n roots. And this is absurd because it contradicts the theorem that we had proven. Okay, so we're gonna have a polynomial with more roots than its degree. Okay, so f and g cannot coincide in more than endpoints. Okay, so two different polynomials cannot coincide in more than endpoints. If they do, it's because they're the same polynomial. Okay, and this is very important for us. Okay, this is very important for us. Two different polynomials cannot coincide in more than endpoints. Observation: if we cannot tell apart two polynomials coinciding in more than endpoints, then this means that a degree n polynomial is completely specified let's write again. Specified. A degree n polynomial is completely specified knowing n+1 of its values. Okay, so there are n+1 constants that completely specify a polynomial. This correspondence between values and degree is of utter importance. Degree n polynomials are in correspondence of n+1 tuples of values. in K. We're going to exploit this very, very much. Okay, so this is of utter importance for us. In this fashion, what we have is we're going to peek into something which is basic for us, which is construction of polynomials. Construction of polynomials with specific target values. Okay, so right now what we're gonna take is an intermediate step. Okay, let's start with an example. Find a polynomial of minimal degree. This is the least possible degree with coefficients in R such that f2 equals 0, f at 3 equals 0. Okay, solution. We need to find a polynomial with real coefficients that has 2 and 3 as roots. Real polynomial with 2 and 3 as roots. Okay, so this is, first of all, this is kind of easy because we can actually define x minus 2 times x minus 3. So this polynomial satisfies what is asked. This polynomial works. Why? Because if you evaluate f at 2, then what you have is 2 minus 2 times 2 minus 3, which is 0. And also because f at 3 can be seen to be computing as 3 minus 2 times 3 minus 3, and that's also 0, right? It satisfies both conditions. Is it the only polynomial? Well, it can be seen that it is not the only polynomial, okay? Let me close this. So if you want to see another version for f, what you do is you just multiply out everything here using the distributive law, and you get the polynomial written as a sum of powers. X squared minus 5x plus 6. So this is the polynomial that we were looking for, which is the same as this one, but this one is written factored. And this one is not factored. Is it the only polynomial that satisfies this? Well, clearly not. We can find a great many other set of polynomials. Moreover, g of x being x minus 2 times x minus 3 times x. When you think of evaluating g, 2 and 3, you get 2 minus 2 times 2 minus 3 times 2, which is also 0. And then you get 3 minus 2 times 3 minus 3 times 3, which is also 0. So G also works. And when you multiply out all the terms, what you get is simply x cubed minus 5x squared plus 6x. Okay, so just specifying the roots of a polynomial does not specify the polynomial. There are many polynomials with the same roots. In this case, f has degree 2 and g has degree 3. So, conclusion. The set of roots alone do not fully determine a polynomial. Okay, we have f and g share 2 and 3 as roots, and they have different degrees. Okay, so there are two polynomials that have 2 and 3 and degrees, but you could object. You could say objection. G has more roots. Than f, because G has 0 as an extra root. You could say, okay, f at 0 is not 0 and G at 0 is 0. So they do not have strictly the same set of roots. So you could object that, and you will be right. So is it the case that we can fully specify a polynomial just with the set of its roots? Well, let's think again. Let's try h of x 4 times x minus 2 and x minus 3. In this case, take a look. The degree of h is also 2, right? H at 2 is also, h at 3 is also 0. And when you multiply out all the factors, what you get is 4x squared minus 20x plus 24. So we have a degree 2 polynomial which vanishes exactly at the roots of f, but they're different. F vanishes exactly when h does. So they share the exact same set of roots, but they're different. And they differ in the leading coefficient. This has leading coefficient 4, and f has leading coefficient 1. All right, so specifying a polynomial requires a little bit more than its roots. Okay, it requires a little bit more than its roots. So we're gonna again a degree n polynomial is completely specified by n plus 1 of its values. All right. So once we have discussed this, we're gonna try to build up on certain idea, which is interpolation. Okay. Let's set up a problem as an example. Find a degree 2 polynomial with coefficients in Q such that f at 2 equals 4, f at 5 equals 6, and f at 8 equals minus 2. In this case, a degree 2 polynomial will be fully specified by 3 values that it takes. Okay, so we're gonna try to do that. We're gonna try to build a polynomial that when we plug in 2, we get the value 4. When we plug in 5, we get the value 6. And when we plug in 8, we get minus 2. Solution. So one strategy will be to solve an intermediate problem. Solve an intermediate problem. Okay, we're gonna find an f1 such that when we plug in 2, we get 4. And then when we plug in 5 and when we plug in 8, we get 0. So we're gonna find a polynomial which is simpler than the one that we were looking for originally. Okay, so we need to build a polynomial which has 5 and 8 as roots, and when we plug in 2, we get 4. So this, we know how to do this. Okay, so f sub 1 of x has to be of the form a constant times x minus 5 times x minus 8. This polynomial f1 will automatically check these two obligations. When we plug in 5, we get 0. When we plug in 8, we get 0. So this is already taken care of. So what we need to do is we need to make sure that we choose alpha, so this condition is met. We need to check, we need to see how to choose alpha so that f1 at 2 equals 4. So this is a design factor. Okay, so what do? We plug in 2 and we will ask that the result is 4. So alpha times 2 minus 5 times 2 minus 8 needs to be 4. And here we simply solve for alpha. 4 times minus 3 times minus 6. This is 4 over 18. So in the end, f1 of x is simply 2/9 of x minus 5 times x minus 8. All right. So this polynomial is a simple polynomial which vanishes at 5 and 8, and it takes the value 4 when we plug in 2. Okay, so we have solved this kind of masking problem in which we address 2 going to the value 4 and 5 and 8 as roots. So we're going to now turn our attention to finding a different polynomial now with 2 and 8 as roots, and that takes the value 6 when we plug in 5. More. Find f sub 2 such that when we plug in the value 2 and when we plug in the value 8, we get 0, and when we plug in 5, we get 6. Okay, so this is, again, easy to do. This will be of the form beta times x minus 2 times x minus 8. So this will guarantee that when we plug in 2 and 8, the polynomial will vanish. And now beta has to be chosen so that this condition is met. And how to choose beta? That's simply just plug in 5 and demand it to be 6. So 6 has to be beta times 5 minus 2, 5 minus 8. And what do we get here? Simply get 6 over 3 times minus 3. That's beta, so minus 2/3. So f2 is completely specified. Finally, we get to the last one. F sub 3 will be a polynomial which will vanish at 2 and 5 and will take the value minus 2 when evaluated at 8. Okay, finally, find f sub 3 such that it will vanish at 2 and 5, and at 8 it has to take the value minus 2. Again, this is easy to find. This will guarantee that it will vanish at 2 and 5, and then we say, okay, when we plug in an 8, we need to get a minus 2. So that means that alpha times 8 minus 2 times 8 minus 5 will be minus 2, and this we will have to solve for gamma. So gamma is minus 2 over 6 times 3. Okay, so minus 1/9. And f sub 3 of x is completely determined. Okay, so the polynomial f we were looking for can be written as the sum of f1 times f2 times f3. This polynomial, first of all, has degree 2. The degree of f is actually 2 because it is the sum of 3 distinct polynomials of degree 2. Okay, and it satisfied all that it is required. Okay, f satisfies f at 2 is 4, f at 5 is 6, and f at 8 is minus 2. Okay, say you want to evaluate this at 2. When you plug in 2 here, you have to plug in 2 in each of these polynomials. This one vanishes and this one vanishes because that's how we constructed it, and this returns 4. So what is happening here is that this f sub 1, 2, 3 observation, f1, f2, and f3 behave pretty much as canonical vectors in R3. Remember when you had the canonical vectors in R2, for instance, and you wanted to write the vector, say, 2, 3. Well, this vector 2, 3 can be thought as 2, 0 plus 0, 3, and this was thought as 2 times the first canonical vector of the basis plus 3 times the second one. This is simply 2 times e sub 1 plus 3 times e sub 2. It's a combination of canonical vectors which take the value 1 in one coordinate and 0 on the other. Well, these polynomials pretty much behave the same. They take the value of a non-zero value in one coordinate and 0 on the others. So this is how we reconstruct f using the same idea. Okay, f is found as a combination of simple polynomials. In this case, polynomials f1, f2, and f3 directly take the values that are asked for the polynomials. But the same approach, the same approach can be given. It is easy to see that we can find polynomials L1, L2, L3 such that L1 evaluated at 2 will be 1, and at 5 and 8 will by the same procedure. We'll have L2 will have roots 2 and 8, and at 5 it will take the value 1, and L3 at 8 will take the value 1, and we'll have roots at 2 and 5. These polynomials L1, L2, and L3 will play the role of the canonical vectors. So now f of x will simply be written as a linear combination of these canonical vectors L1, L2, and L3. Simply by saying, okay, I want to take the value 4 when I evaluate at 2. I want to take the value 6 when I evaluate at 5, and I want to take the value -2 when I evaluate at 8. So what we have just done, building F1, F2, and F3, can also be seen as building these canonical polynomials and combining them to find f. So what we have done is we have built f using Lagrange interpolation. L sub I is the ith Lagrange polynomial for the correspondence and they play the role of the canonical vectors. Okay, we're gonna finish with this example, and we're gonna talk about the specifics of the Lagrange interpolation procedure in a different video, and we're gonna think for the future first of all, formalize this. Second of all, we're going to think of the role of the number of elements in K. And third, we're going to think about probability of choosing a specific polynomial when picking at random. Okay, so these are the following steps in our polynomial endeavor. Okay, so I hope you liked this video. I hope you watch it as many times as you need it, and we'll see you in another episode for mathematics in Lambda class. Okay, goodbye.